Welcome to this new video about semiconductor physics. Before we delve into all the important topics of semiconductor physics that are relevant to solar cells, we need to talk about silicon. Silicon is one of the most important materials when it comes to solar cells, and we will be using it throughout this video series as an example for all the semiconductor concepts we will be going into. This will only be a short introduction to silicon, and there will be an extensive video series on silicon-based solar cells in the following course, Photovoltaic Technologies. Let's start our discussion by looking at the reasons why silicon is the most used material for fabricating solar cells. The first successful silicon solar cell was fabricated in the Bell laboratories in the US in 1954. At present, the photovoltaic industry is dominated by silicon-based solar cells, with 90% share of the market. Silicon is the most widespread material used for solar cells. But why is it that silicon is used so much? To start with, silicon is the second most abundant material on our planet. This is important because in order to make solar energy a large player in the global energy landscape, we are going to need a lot of material, so we need a material that is abundant. Secondly, processing of high-quality crystalline silicon is very mature, since it has been used in the microelectronics industry for decades. This means that we can produce a material with very good electronic properties. Moreover, silicon has optical properties which are close to ideal for absorbing visible light, making it a good candidate to convert solar energy. Now that we know why we use silicon, let's take a look at its atomic configuration to start to understand a bit more about this material. The silicon atom has an atomic number of 14. This means that it has in total 14 electrons orbiting around its nucleus. The electronic distribution can be better visualized if the atom is represented with the Bohr model. We can see that there are 2 electrons orbiting in the first shell, characterized by quantum number 1, filling only the s orbital. In the complete second shell, 8 electrons are filling s and p orbitals. The third shell is not completely filled. There are only 4 electrons in the shell, 2 filling the s orbital and 2 are present in the p orbitals. The 4 electrons present in the third shell and characterized by quantum number 3 are called valence electrons. These valence electrons are responsible for the formation of chemical bonds between the silicon atoms. So the questions now are, what kind of chemical bonds do form between silicon atoms, and how many neighboring atoms are there to a single silicon atom? As you can remember, chemical bonds arise from the interaction between atoms. They can be formed by sharing of valence electrons or as a result of the electrostatic attraction between charged atoms. An atom forms bonds with other atoms in order to achieve most stable electronic configuration. This configuration is characterized by having the outer shell orbitals filled. In chemistry, this situation is called the octet rule. Silicon has in its ground state configuration 4 valence electrons. 2 electrons occupy the s orbital and 2 are located in 2 p orbitals. However, silicon, like carbon, when creating bonds, prefer to form 4 orbitals of equal energy. These orbitals are called hybrid sp3 orbitals. To achieve the lowest energy configuration, electrons will fill separately one orbital each. Now, every unpaired electron can be shared to form a chemical bond. Silicon can form 4 bonds, and it is therefore said to be 4-fold coordinated. Let's visualize the bonding process using the Lewis representation of the silicon atom. When other silicon atoms are present, they can interact and form bonds by sharing one valence electron with a neighboring silicon atom. These kind of bonds are strong and they are called covalent bonds. In the representation known as bonding model, these bonds are shown as straight lines connecting 2 atoms. What we have just seen is fundamental to understand the physics of a material. Let's now move a step forward towards the description of silicon as a semiconductor material. Silicon is present in nature as a solid. Silicon is to be found in silica and silicates compound materials. However, for semiconductor applications, silicon has to be mainly in crystalline form and very pure. It means that silicon atoms are arranged in periodic, regular way with long-range order and without impurities. A solid can be either monocrystalline, polycrystalline, or amorphous. Monocrystalline solids are highly organized structures where atoms form a continuous crystal lattice. However, in polycrystalline solids, regions of crystallinity are present with different sizes and orientations. These small crystals within the lattice are called grains or crystal domains. Nevertheless, the presence of grain boundaries makes the lattice non-homogeneous and not continuous. Lastly, amorphous solids are materials in which no crystallinity can be observed. It is important to realize that the way atoms are arranged has a great impact on the material properties, both physical and optical. As a result, it will affect the performance of a device. For solar cell applications, we are mainly interested in crystalline solids. In a crystalline solid, we can identify a unit cell or a lattice unit. This is the smallest organizational unit of the whole crystal lattice. The crystal lattice is constructed by repeating or adding the unit cells together. In the case of silicon, this unit cell is similar to the one of diamond. With 8 atoms contained in the volume of the unit cell, we can also derive the density of silicon, which amounts to 5 times 10 to the power of 22 atoms per cubic centimeter. Macroscopically, this is how monocrystalline and polycrystalline silicon wafers look like. The differences are clearly visible. In the first case, the lattice is characterized by very long-range order over the whole wafer. On the other hand, in polycrystalline silicon, we can observe several crystal domains. These domains are still large enough in the range of centimeters. The boundaries between the domains can be seen as defects, and they hinder the charge transport within the material. The presence of grain boundaries decreases the electronic quality of material and influences the performance of solar cells. This video was aimed to introduce silicon, the most used material in solar cells, to you. We have seen how silicon atoms bond together to form crystals. We learned that the size of crystals in the material has an impact on the performance of a device. In the coming videos, we will discuss the main important aspects of semiconductor physics that are relevant to solar cells.